start this afternoon session with Eduardo Novais from Federal University of ABC.
Thank you very much. Thank you for the organizers for the opportunity to present this work. And I work at Federal University of ABC, which is a federal university about 30 minutes drive from here. So it's not really São Paulo, but it's nearby. And ABC is because it's the first letters of the three cities that make the region. And so it turns out that we are in this frontiers in quantum materials, but we didn't talk about devices here, right? So we have many presentations about materials and then about devices. So what I'm trying to convey here and try to explore is that, well, we are in these days of quantum technologies where we see these beautiful pictures, but mostly we use traditional materials to build them. And can we do something different with quantum materials and interesting materials? So the lab is very hard, and as you can see, can be very messy. And so for a theoretician, it's for me, I draw beautiful pictures, nice pictures, and the lab can be very different. But anyway, so the simplest possible device that you can construct, right, is a point contact tunneling device. And here is an example with Hall edge states. And this will be an interesting idea if we can use it with advanced materials, with different materials. So what I'm going to talk about is that using topological edge states. Why? Because they are protected by time reversal symmetry, which suppress backscattering. And inside this ballistic transport regime, we also have well-defined helicity, right? The spins go up, goes in one direction, the spin downs go in the opposite direction. So can we build something that is interesting with that? So that's the main idea here. So can we build devices with topological insulators? And so there are experimental results out there. So for example, you can construct edge states using carbon-coated cantilevers. And here you have a beautiful picture where you can actually construct these edge states using scratching your material, right? So these edge states are the main block, building block that I'm going to use here. So you also can gate these materials. So this is an example where you can have a transition from a semi-metal to a topological insulator by gating. And so in addition to build the material, scratching it, we can also use gating in order to produce the devices and the regions that you would like to be topological and non-topological. So what are the properties of edge states? Which one? No, this is scratched. They scratch the surface, and then they have certain. I think I have the picture here. So this is a drop. They have an edge state in each one of these these lines. Not a whole state. There's no magnetic field. You have the topological insulator edge states there, right? So you have. I'm going to describe them right now. So you're going to have spin up going in one direction, spin down going in the opposite direction, and a Luttinger liquid in each one of these lines here. So what are the properties of edge states, right? So it turns out that you don't have backscattering, but you can have forward scattering in your materials. And here is an example of a material where you do have a very large electron-electron interaction. So it really behaves like a Luttinger liquid. And you have a very strong Luttinger parameter, which is one would be a non-interacting Fermi gas. And here we have below half, which is a strong electron-electron repulsion in your material. That happens here at the edge. So the bulk is insulating, but the edge can conduct and behaves like a Tomonaga Luttinger liquid. Right? So you can also use proximity effect to induce attractive interactions between your fermions, and therefore you can play with your G parameters from a very strong repulsive interactions to a very strong attractive interaction between your fermions in the edge. So what are the basic devices? So this was explored a long time ago by Claudio Chamon, which are at point contact tunneling between these helical edge states. And there is a very interesting phase diagram when you can have insulating phases or conducting phases depending on the interactions in the charge sector and the spin sector of your fermions. But here I'm going to talk about a Y-junction. A Y-junction corresponds to 3 edge states. So you have 3 edge states connected to 3 different contacts. And now you have tunneling, possibility of tunneling between any one of these 3 edge states, right? So the basic assumptions that I'm going to do is that, well, we can actually use bosonization or a field theory description for the edge states. There is a specific geometry that I chose because it's the easiest one, but you can play around with that. And the tunneling process, they preserve the spin projection, so there is no spin flip during the process, which seems to be reasonable, at least for certain materials. And finally, there's some technical part which is related to the hopping amplitude of correlated pairs. So why I started studying this? Well, because more than 20 years ago, I learned from Claudio and Ian Affleck about Y-junctions. They were studying this in a different setup. They were studying 3 wires, and they consider having a magnetic flux in the middle. So they have 3 quantum wires connected to this magnetic flux. Shaitan Nayak also studied this similar setup before without the magnetic flux, but with an island between the conducting wires. So why this is interesting? Because you can have very weird conductance tensors related to this geometry. And in the case of Ian and Claudio, they found some very interesting renormalization group fixed points for your theory as a function of the magnetic flux. So here they are considering attractive interactions between their fermions, and they found 2 chiral points where your current flows completely in one direction from one wire to wire 1 to wire 2, from wire 2 to wire 3, from wire 3 to wire 1, or vice versa in the opposite direction. There was also a fixed point they couldn't understand very well because it's time reversal, and this is they call mystery or M. And but it was mainly for attractive interactions. All the interesting part came when you did have attractive interactions between your fermions. So this is basically the general setup that they consider, and they found the disconnected fixed point, the chiral fixed point, the Andreev reflection-like fixed point where you have pairs of fermions hopping around from one wire to the other, and then you can have a large conductance here. And then the mystery fixed point, which is time reversal, and they didn't understand quite well some of their properties. So why considering this using topological insulators? Because the main idea that drove me to look at this problem was to, instead of having this external magnetic field applied to your wires, to use the inherent spin-orbit coupling to provide the external magnetic field, this internal magnetic field, and try to realize some of those fixed points that Affleck studied before, Affleck and Claudio studied before. And so we have a playground with interactions in general, right, which can cooperate or compete with the spin-orbit coupling to give you a general setup for complicated systems, and I hope to find something interesting here. So the general idea is that you have your Fermi liquid contacts, and then your electron will hop to the edge states, will move around, and then will hop to another edge state, and eventually goes to the drain in your Fermi contact somewhere else. And so the basic calculation is try to find what is the conductance tensor for this geometry in this setup, right? So in order to have some idea of how to work and what are the phases that are, or the magnetic fields, the effective magnetic fields that I'm considering, I look at a very specific geometry, and then I consider the Kanan-Malley model, where you know the standard band theory, you have your edge states, you have your band gap, and in addition to that, you will also be opening this gap, you have this second nearest neighbor hopping, which is complex. And this comes from your spin-orbit interactions, and that's what provides your internal magnetic field to your sample, right? So just to have some feeling, you can do some basic tight binding calculations, and you realize if you apply a gate in part of your sample, then you do create an edge state, which is here represented. So this is the parameters that were chosen to draw this picture where you do have the edge state here, right? So the geometry, the basic geometry here is that you have these 3 edge states, and then you have the hopping between your edge states. We introduce forward scattering and treat the edge states in the Luttinger liquid behavior as using bosonization. And then you have the interaction, the forward scattering interaction, G, which is larger than 1 for attractive interaction and smaller than 1 for repulsive interactions. So the tunneling Hamiltonian now has to consider the phases that you get because you are writing your second nearest neighborhood hopping with a complex number. Then when the electron hoppings from here to here, it does get a phase, just like having an external magnetic field, and that was considered by Affleck and Shimon in Ishikawa. So in this example, for example, it gets a 2 phi when it hops from edge 1 to edge 3. But as I said, you can change this geometry and do something else, right? So as I said, attractive interactions for G larger than 1, G equals 1, no interactions, G is smaller than 1, repulsive interactions. And as I presented, it seems that experimentally large repulsive interactions, G smaller than 1/2, are possible. So there are several tunneling processes that you have to consider. This first one is single electron tunneling, where an electron tunnels from one edge to the other, preserving its spin. And this is the kind of form that you have. But it turns out that this is an irrelevant operator every time that you go away from the non-interacting fermions. So the next possible tunneling mechanism is correlated spin flips, where a spin up in one wire goes from wire 1 to wire 2 at the same time that a spin down goes in the opposite direction, right? And this can be relevant or irrelevant, but because the electrons move in the opposite spin, move in the opposite direction, you get an extra phase 2 phi, 2 times r phi that you had before. So this is the kind of mechanisms that will create this internal magnetic field that I was discussing. The next possible correlated tunneling is correlated pairs. You have a Cooper pair-like pair, and it tunnels from one wire to the other. And this one has no internal field because the phase that the up spin gets, the down spin removes. Right? So the weak tunneling regime, you can do renormalization group calculation, and then you realize, well, the single electron tunneling is irrelevant always. These correlated spin flip events, this one is actually irrelevant also from G 1/2 to G equals 2. And the same thing for the correlated pair tunneling. So you have a whole region in parameter space where absolutely nothing very interesting happens, right? So for small interactions, you can do renormalization group, perturbation theory improved by renormalization group, and then you realize that your conductance goes to 0 as some power of the temperature depending on your G parameter. But your fixed point, renormalization group fixed point, is always the disconnected wires. The thing interesting happens when you go for a larger G, right? When you are in a very strong repulsive regime or very strong attractive regime. Right? For these fixed points, the disconnected wires are unstable, and you go to some other place in your phase diagram, right? So this is kind of a summary of this part of the phase diagram, and you realize you have a renormalization globe flow to the disconnected wire from 1/2 to 2. But then for larger than 2 or and smaller than 1/2, you go to strong coupling. And here you have the corrections to the zero conductance due to temperature fluctuations. Right? So now we're going to try to explore what happens in these two regions of strong interactions. So the weak barrier limit was done, and now we go to the strong fixed point, which you have to minimize the hopping terms. So you go to a classical, semi-classical analogy study, and you try to minimize this function here, which is the potentials that your tunneling Hamiltonian fields presents. And then you try to minimize this potential, and then you do an incident calculation that tells you from one minima to the other minima. So you build up a dual theory, and turns out that depending on this phase phi here, it's phi bar, you can have two minima structures. You can have a triangular lattice, or you can have an hexagonal lattice for specific values of this phi bar. And they produce two very different phase diagrams in your theory, depending on this parameter phi bar here. So for G larger than 2, you don't have the external phase, and everything that you have is this triangular lattice for the minima of your cosines. And it turns out that the dual theory has this form and is stable for all G larger than 3/2. This creates kind of a funny picture, right? Because I said that the weak coupling fixed point was stable for until 2, but now the strong coupling fixed point is also stable for 3/2. So there is an intermediate fixed point that is unstable somewhere between 3/2 and 2. So, but what is the physics of this strong coupling fixed point? This is exactly the Andreev reflection, where you have a pair of electrons that hop together to another wire. So you end up with these theory and dual theory, and you have a self-dual point at G equals square root of 3, and you realize that the physics that you find here is exactly this three-state Potts model for from conformal embedding. And what you got is that you have an unstable fixed point from 3/2 until 2, for G equals 3/2 until 2. And I'll show a phase diagram in a few moments. But now let's look at the other theory for G equals 1/2. For G equals 1/2, is smaller than 1/2, you have the phase that comes from your hopping of your spin tunneling event. And now, depending on this phase here, you have a triangular lattice for the minima of your potential, or a hexagonal lattice. So let's first explore the triangular lattice, because this is exactly what we had before. For these phases here, you pretty much reproduce what you had before. And you have a dual theory, and this dual theory is stable for G smaller than 2/3. So you have the theory and the dual theory. Again, it's related to three-state Potts model for the, and you have a self-dual at G equals square root of 3/3. So the strong tunneling, for this set of phases, you have an unstable fixed point from 3/2 until 2, and then you have the Andreev reflection and the disconnected wire here. And for G smaller than 2/3, you also have an Andreev-like fixed point, and then the disconnected wire below here, right? And an unstable fixed point. The interesting physics comes around now when you have these phases here. When you have these phases, the minima now is an hexagonal lattice that comes from having your two triangular lattice becoming degenerate with each other. And this hexagonal lattice now produces a stable fixed point. You go and you build your theory, and you realize that you have a relevant flow for G smaller than 1/2, and a relevant flow for G larger than 2 2/9 in the dual theory. So there will be a region where you flow from weak coupling and you also flow from strong coupling to an intermediate fixed point. I'm sorry? No, this lattice is the potential of the cosine of your hopping terms. So the idea is that, okay, every time that you hop, you will have one of those cosines in your bosonic theory when you bosonize the hopping Hamiltonian, right? And so now you have x and y in space, and you try to, which is phi x and phi y. You have a dual. Your theory is two-dimensional because you have to take into account you have 3 bosonic fields, one for each wire. So it's and you have to conserve charge when you tunnel. So in the end, you have 2 bosonic fields to minimize. I have one-dimensional problems in each one of the edge states, but but each one has a bosonic field. So you have 3 bosonic fields, but you have to conserve charge when you cross the junction. And when you conserve charge across the junction, you only have 2 bosonic degrees of freedom. And so that plane, or hexagonal or triangular lattice, is the minimization of that potential of your 2 bosonic fields. So now the picture becomes a little bit different, because now you still have the disconnected wire that goes from 1/2 to 2, but for interactions, strong repulsive interactions, you have a stable fixed point from 1/2 until 2/9. So what is the Y-junction conductance? Well, the Y-junction conductance, well, this is a general tensor for your conductance, and you have a symmetric part and an antisymmetric part. The symmetric part is 0 by time reversal, and this is the thing that that wasn't clear when I started the presentation, is that the topological insulators are time reversal symmetric. So the antisymmetric part cannot exist in your tensor. And therefore, the chiral fixed points that Ian and Claudio and Oshikawa derived cannot be realized in this particular geometry because of time reversal. So the wires. So can be plus or minus 1. It's not the antisymmetric tensor. No, it is the there's no. It is no, it's the antisymmetric tensor indeed. It's the antisymmetric tensor. There's one term missing here. There's
so the plus or minus is there, or should be plus?
Should be plus.
Okay.
Yeah. It's funny. I didn't realize that. Okay, so let me just summarize what we had here. You have 2 possible phase diagrams, and you have charge tunneling for large attractive interactions, and you have spin current or spin tunneling for strong repulsive interactions between your electrons, your fermions. And as you go down in temperature, right, you expect that your triangular lattice in the potentials, they start very different. If they start very different, then they should be the triangular form in general. But if they are very close to each other, they start at an hexagonal lattice, and then eventually they move towards a triangular lattice. So there's a crossover for general phi from this picture to this picture here. And then you have the conductance. You can be evaluated in certain parts of your phase diagram. First, you can look at the no-interacting points, right? So you have no-interacting electrons here, and you have 8/9 E squared over H for each channel that's tunneling. Or you also can refermionize in G equals 2 and G equals 1/2, and also calculate the scattering matrix, and realize that you're going to have 8/9 E square of H of conductance maximum, right, in each one of these two no interacting points for your Y-junction. The Andreev reflection can have a conductance that is even larger than the maximum conductance for single electrons is 4/3 of E square of H, and this comes from the unitarity. And it was derived first by Chaitanayak, I think, in that paper that I mentioned before. And you also have the self-dual points, which is another place that you can also calculate exactly your conductance as 2/3 E square over H. So the picture that you find is that in the self-dual points, you have this 2/3 E square of H. You start with 0, and then conductance here, and then it goes up until it gets to 4/3 E square of H in the strong tunneling limits and the Andreev reflection. So topological insulators then seems to be useful for devices, and maybe other geometries can realize the Y-junctions that Claudio was talking about, and Claudio and Ian and Oshikawa were talking about. And why they are interesting, at that time, 20 years ago at BU, they were thinking about spintronics and the possibility to use it to actually promote create some form of transistors at that time. So hopefully, although we don't find the Cairo fixed points here, hopefully another geometry may be useful to find this fixed point. Anyway, there is a stable RG fixed point, which is non-trivial for strong interactions, which is in the relevant experimental region in the parameter space. And I would like to thank Claudio Oshikawa and Ian Affleck for showing me this problem many years ago, and to introduce me to the idea that the geometrical position of those wires can introduce very interesting physics that is related to other things that at that time I was considering, which was the Hofstadter model and quantum Brownian motion. Thank you.
Thanks, Eduardo. Questions, comments, criticisms?
Very nice talk.
Thank you.
And I was curious about the spin flipping terms that you mentioned very briefly. You would not consider?
I didn't consider any spin flips because experimentally they don't seem to be there, at least for the mercury.
But from basic physical grounds, they could be there.
They could be there, right?
Yeah.
They could be there. But
Because
wouldn't
since you don't
conserve
have
the
a
tunneling-
magnetic field.
Yeah, it wouldn't conserve the spin as it crosses. And it's possible if you have impurities or something else in your sample, right, that you don't conserve the spin projection when you tunnel across the junction.
I would actually think that generically they would be there.
Probably, but as I said, they didn't find it experimentally, and that's why, for example, in that paper that I talked about, that I showed of the point contact tunneling calculated by Claudio, and another one by Kane, they didn't include the spin flip terms in their description.
Yeah, but do you have any intuition what they
What
could
come
do
out?
with the phase diagram if you would?
No, I didn't calculate that. And in fact, I was really interested in trying to find the Cairo fixed points, but it ends up that since we are in this time reversal point, I end up found that mystery fixed point. That my stable fixed point is that mystery fixed point from Affleck's paper, and the one that they don't know very much about.
Okay. I was also curious about the Hofstadter part. I saw it in the title of one of your slides.
Yes, the Hofstadter.
But you ended up not talking about that, and at the end you said that that was the original motivation.
Yes.
So maybe you would like to elaborate a little bit on that?
Sure, thank you. Thank you for the question. So the idea is that when all these problems of junctions and hoppings can be understood in terms of quantum Brownian motion. So when you have that lattice, the hexagonal lattice or the triangular lattice, I can think of that as actually I have my minima, which is my random walker, and it's hopping from one side to the other. So traditionally, you have this discussion in quantum Brownian motion, and you know that these kind of lattices can lead to very strange phase diagrams. But in the late 90s, early 2000s, Denise Fried and Curtis Callan developed this idea of the dissipative Hofstadter model, which is to have the quantum Brownian motion in the presence of a strong magnetic field. And then you realize a very weird fractal phase diagram. So when I started studying this thing, I was worried about that. And it turns out that Claudio and Ian, when I was at BU, they were also working at that problem, considering the Hofstadter problem. Why? Because with the Hofstadter description, they could find out the properties of their chiral fixed point, mapping from the original problem to this dissipative Hofstadter model that Callan and Denise Fried developed a few years before.
All right. Thanks a lot. We have
Thank
to move
you.
on.